Hello, my name is Janet Callahan, and I would like to help you learn a little bit about bonding force curves as well as bonding energy curves. So let's begin by developing a bonding force curve. We're going to draw a vertical axis and a horizontal axis corresponding to 0. Above 0, we would have a positive bonding force. Below 0, we would have a negative bonding force. And the horizontal axis is distance, and far out there on the far right, we would see infinity. So I'd like us to envision sodium chloride as an example of something that's bonding. Now for sodium chloride, I believe the smaller atom is sodium, and chloride ions are a little bit bigger. And so when sodium, I'll just write a little Na here, and Cl, when sodium chloride are in equilibrium with each other, we would expect the net bonding force between them to be 0 because they are at equilibrium. And in fact, that's an important part of the bonding force curve. And if there's a piece I'd like you to remember, it's that the bonding force curve kind of comes through 0 with a almost a straight line slope. And so to kind of complete what the bonding force curve looks like for something like sodium chloride, almost any atom, we see it does something like this, and kind of goes out to 0 at infinity. So that black curve is actually the sum of two other curves. The first thing it's a sum of is an attractive force, and for sodium chloride, so I'm going to draw kind of a big purple dashed line. We have an attractive force, and the origin of the attractive force for something like a sodium ion and a chloride ion would be Coulombic attraction, just opposite charged particles will attract each other. And so this attractive force, literally predicts that they'll be so attracted to each other as to lie on top of each other. But that can't happen because there is a repulsive force that comes about as a result of the ion cores. The cores that, the electrons don't want that to happen, and so there's a repulsive force that I'm depicting with this red dashed line kind of going there. So so if I label the attractive force Fa, and then I label the repulsive force Fr, then the black curve, the net bonding force curve, is going to equal the sum of these two, Fa plus Fr. And so the shape of the curve, to kind of lock in your memory, is that the bonding force curve does something like this for pretty much any material, whether or not it's an ionic solid. And so let's kind of dive in a little deeper toward what's going on at the origin. So as we discussed last time, and now I'm shifting plots, I'm now going to just throw this back into your memory. When we discuss the experiment of pulling on a part, where stress is force per unit area and strain is equal to the change in length of the part per original length, and where the experiment is simply pulling on a part with a tensile force F across a cross-sectional area A. So when we pull on a part, what happens is that the part, which is originally with no extra elongation, the part gets longer. It gets longer elastically. And the slope of this, remember, we call the Young's constant. We give it the symbol capital E. And so the equation to remember, and again, this is chapter 7 stuff, is that stress is equal to the Young's modulus times the strain. In other words, y equals mx, and of course it's going through 0. So bringing our attention back to the bonding force curve, notice that it's linear whether it's an attractive force or it's linear through this range of 0, both on the positive side and on the negative side. And so for positive stresses, we see that the part gets a little bit longer, but also for negative stresses, right? We could, instead of pulling on it, we could exert a compressive force F and just reverse the direction of F, and now it would be under compression because it would be being pushed upon. And under compression, it's also linear, and it would have the same slope. And this is true for when we do this experiment on metals, on ceramics. They are linear in their elastic regions. And of course, if we pull upon it too much or compress it too much, it is not linear. All right, so this segment was focused on this important concept of the fact that there is a relationship between the bonding force curves and elastic behavior, let's call it that. Because the F versus distance curve is linear near net bonding force equals 0, comma, I guess the mechanical behaviors of the part is also initially linear. All right, thank you for your attention. I hope you understand bonding force curves and the relationship of these bonding force curves to elastic behavior.